Okay, in this tutorial we're going to have a look at interference, constructive and destructive. We're going to see how that applies to the dual slit experiment later on, and we're going to see how it's using diffraction to enable this to happen, to give us coherent waves. So the first thing we need to get right and understand is having two waves which are both starting off coherent, and in the same space they are literally twice the energy because the amplitudes add. Let's put them underneath each other. If you offset this by a wavelength, they continue to add. Don't forget, the waves are continual in both directions because they are functions. So as long as you have lambda, let's draw the lambda in. As long as you have the wavelength shift every time that you shift by lambda between two waves, you get a situation where the waves combine and add. That is constructive. It constructs more, it makes it bigger, hence constructive. Let's try and get that in the right position. There we go. There is a wavelength or lambda shift. So let's have a look at what happens if we end up with a lambda over 2 shift between the waves. Let's put that up there. Lambda over 2. This is a different situation. You can see now, I'm going to do the shift. If I make the lambda over 2, it means they're kind of in antiphase with each other. So basically, when it's low, it's high, and when it's high, it's low. And any point between the two cancel themselves out to give you a resultant wave of zero displacement, which means it is dark. There is no all the light energy has been cancelled out, and that is called destructive interference. And I'm not writing it out for. Okay, so they're the two kinds of interference based on the position. Bear in mind, it's the same for both of these. If you move it as far as you like, but in multiples of half a wavelength, you'll always get destructive interference. If you shift it from a constructive point by one wavelength at any time, as many times as you want, it's always going to land in a position where it will be constructive. So it's basically continuous, it doesn't stop. On this slide we're going to have a look at path difference. This is what gives us the different spacing between the two waves. So this is what gives us the wavelength difference in translation, or the wavelength over 2. The first example here is 2 points from which waves are being transmitted, and we are observing the wave at a point that is exactly equal, split down the middle from both points that are being sent. So let's have a look. This is receiving. Now these are being sent, and these waves are coming in along this path, and these will be coherent at every point because there is no difference in path. No difference in path because everything's even. They have the same distance. So now we need to consider the situation where the path is different. So now we put the receiving or the observation point up here, and the top one has got a shorter path than the blue one. So the red one is shorter than the blue one. If that difference is lambda, or the wavelength, it will be bright. If it's lambda over 2, or half the wavelength, you'll get a shift that means everything is cancelled out and eliminated. So basically it's all about differences in path to where the waves are going and where they're being observed from, and this is what sets up the interference pattern with the dual slit experiment. This is the whole crux of it. So just to reinforce this situation, if there is a path difference due to the fact that they are going different lengths depending on the angles they're going between being sent, transmitted, or received, you end up with lambda over 2. If it's lambda over 2, if it happens to be lambda over 2, you get a dark stripe and you get destructive interference. If that path difference between the red and blue is a lambda, a 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda, up to whatever lambda, n lambda, you get a bright constructive interference effect.